Hey, good morning, everyone. My name is Morokot from Florida Tech, and on behalf of my co-author, today I would like to share our work on real-time estimation of drag-based parameter and Leo using adaptive control and sparse identification. So the main idea of the study is we want to improve the adaptive control concurrent learning and allow it to do sparse identification technique. So this is the content of my talks. So I will start with the motivation why drag estimation is hard but important in low Earth orbit. Then I will describe the problem setup, and I will propose a controller design with the stability analysis using the Lyapunov-based approach. And after that, I will describe the simulation setup and result. Finally, conclude with key takeaway and future work. So as a motivation, because we will deal with differential drag, so I will start with defining differential drag. So this is a relative acceleration caused by different atmospheric drag acting on two spacecraft. And this is a formula of drag, and this is how we compute the differential drag. And in low Earth orbit, this can be useful as a problemless way for station keeping, or it is an important disturbance to be considered if you want to do accurate proximity of operation. However, the challenge is that estimating drag is difficult. For example, the atmospheric density actually depend on space weather or the drag-related properties such as area or this coefficient sometimes depend on the geometry of the spacecraft, and it is time varying and also only approximately known. So far, there are many common strategy, but also have some limitation. For example, there are a data-driven method that we can do some regression. However, it requires a large set of data and some repeat computation that is not ideal if you want to do it for onboard usage. The other methods, such as adaptive control, allow onboard use, but it's very sensitive on how well we be able to model the drag itself. So the objective of the study is we want to propose an online sparse identification technique that only require minimum data and computation. All right, so moving on, I would like to first start defining the problem setup. So we will consider a pair of satellite, a target and a chaser, flying a low Earth orbit, and we will be expressing the relative motion in the LV frame that are attached to the target. So in this work, we decided to use the Clobert-Shear equation that have the compact form as the following. And n is the mean motion, and then x is relative position in early Earth frame, and then u is a differential control input. In this example, it is applied only to the chaser. I want to emphasize that even though we use Clobert-Shear equation in this example, this proposed strategy that we're going to propose from now is not actually tied to a specific model. You can also apply to other model, or it's not even tied to this dynamic. It's just an example that we know in our research group. So that's why we decided to use it as a way to validate our proposed design. So going back to the question, so the key term that we want to look at right now is this red color here, that is differential drag, that we would like to estimate online. So in order to design, because the problem is actually designing adaptive control, so we need to derive this differential drag form into this linear parameterization that is depend on y and theta, where y is the known part and then theta is the unknown part. So next problem that we need to deal with is how do we actually express this unknown? How do we model this unknown? So this slide shows the concept of how we model this, but I would like to first discuss about SINDI, because SINDI is the method that we borrow from to actually model the unknown differential drag. So SINDI stands for sparse identification of nonlinear dynamics. And the idea is that SINDI is the technique to discover a sparse dynamics of any dynamics equation that we only need a few active term from a large nonlinear library. And the way it works, and also it's also the limitation of SINDI, is that we need to collect a large bunch of data that can depend on state and input. And we need to run an offline sparse regression that the method called threshold least square to identify this coefficient. So in our case, we want to do this online. However, we're not trying to replicate the method of Cindy. The part that we borrow is that we are assuming that the unknown differential drag that we want to model is actually came from a large non-library of function, and we assume the controller will be able to just select a few active terms from there. So to do that, now we need to rewrite this regressor using the set library that we wanted to model. So we start from a measure known signal and then come up with our own library of function. In this case, we want to simplify a little bit. So for now, it only require a velocity term of the chaser and the target, and the periodic term that is sine, cosine, that is depend on the target mean motion of the target spacecraft. And with just this possible combination, which is 2 or 3 candidate term, by combining them together, we come up with 18 of candidate term. And in order to form regressor, you need to apply the canonical delta, which is for x and y, z. So that means that now the regressor now have 18 multiplied by 3. So it's actually 54 term that the controller need to actually start with. And then the main idea is now the controller need to be able to discover that only a few of them that is actually important, and actually the term that important to express this unknown coefficient. So now the key important idea is that how do we be able to make and design a controller that be able to do this? That is what I will propose in the next few slides. All right, so before we start talking about that, let's now first talk about control design. So I will introduce XD as the desired trajectory and then define the tracking error, E and E dot as the following. And now we need to define auxiliary state error R that is now depend on E and E dot and alpha E. And next is we need to define the 2 type of unknown coefficient, because the first one is a full library of coefficient that is just data. And then once the controller discover the most relevant term, we're going to call it theta S. And beside from that, the hat symbol mean estimation, and then tilde, data tilde mean estimation error. And from this, now we can form our control objective. So the first part is we want the error state to converge, and at the same time, we want to identify the sparse coefficient of the unknown part. That mean the sparse coefficient, and that mean the data S tilde will also go to 0. So from this, we can use relative dynamics to actually obtain the open loop error system or that have the following form. And finally, to be able to do this sparse regression, we need to formulate a 2-stage controller that composed of 2 stages. The first stage is called warm up, and the main idea is that we need to determine the most relevant term. And then second stage is identification state that makes sure that we ensure the conversion of all the state and estimation. So how do we do that? How do we be able to determine the most relevant term? So the key idea is actually how we propose the Lyapunov function. So in order to enforce sparsity, we need to introduce this term called Bregman diversion term into the Lyapunov function. So let's look at this Lyapunov function that we have over here. So the first 2 terms is related to the state. That is a conventional standard quadratic term that is standard in adaptive control. And the only part that we change here is that we now introduce this Bregman diversion term that still measure the difference between the true and the estimation. So it's actually the estimation error. But now this is a generalized distance that have the following formula. And now it depends on this convection function psi theta that we can propose. So if we propose so now you have a series of geometry function that you can input into this converge function. For example, if you use a L2 function, now it will become just a quadratic term that you see normally in the Lyapunov definition. But in our case, before we want to promote sparsity, we want to only select some term that's important. It is well known that the L1 function that have the following formula is actually be able to promote the sparsity. That's why we select this L1 function. And this L1 function is actually depend on the square of this um, estimation. But actually, if you remove this data, it's actually a uh, absolute value of each of the estimation of the unknown data. And we need to add the small data is just to make sure that it's smooth. So after we proposing this uh, L1 function, now we can do time derivative to actually plug it back to the Lyapunov function. And you can see that now this time derivative actually depend on two terms, which is the Hessian of it, that is defined as the following, and the rate of change of the estimation of the unknown. And we need to propose this rate of change, which we call adaptation law, that I will talk about in the next term. But the key term, that the key idea from this is that now when we propose this uh, adaptation law or the rate of change of this estimation, it will be depend on the reverse of this Hessian that we call Bregman gain. And this Bregman gain will help us freeze the zero coefficient that is not important and will amplify the update of the more active term, make it adjust more so that it can separate between the zero coefficient and then the active coefficient. So let's look into that. How does it work in that case? So this is the more detail on the two-state controller. So this is a timeline of all the state that it's gonna go throughout the simulation. So the first one will be the warm up. And this part will just calculate the state and actually be able to adapt the full unknown. And at the end of the day is to rank the active coefficient. And we need to propose the controller. This controller is actually a standard way that you will see in adaptive control. So I will not talk more about this. But the main part here is that this adaptation law, which is called the gradient-based adaptation law, is still having do this Bregman gain into this coefficient. So what does it mean in this Bregman gain? So now this Bregman gain will act as adaptation gain. It means that now because this rate of change is now depend on the actual magnitude of the estimation. So it means that if the estimation is actually small, start with zero, that is not active at all, it will gonna stay freeze at zero. And if it actually active, which is changing, this rate of change will also help encourage it to move even faster. So that means that this part will be able to discover what is active term and not active term. So at the end of this stage, we will be able to select an active term from the from the full set of coefficient. So now we move on to the stage two, which is identification stage. So the control law and adaptation law will look similar, but now we only use a subset of the active term that we discover from stage one. So we can see the controller will look the same, except that now we only use the active term. And then the adaptation law now depend on two terms. The first one is similar to the last one, it's just the gradient-based term, and second one is called concurrent learning term. And this concurrent learning term now includes some summation that collecting input and output of the uh, input and output to actually learn about the system. And the key idea here is that we only enable the CL term when we collect enough information about the system. So how do we check when we collect enough information? Is that we will include this condition called finite excitation condition that actually compute the eigenvalue of the square of the not so the summation of the regressor, and we can define this user defined value that set when we should enable the second term, and then the second term will help us drive the estimation error to go to zero. In this paper, we also prove the theory, the stability analysis for each of the time interval that we talk about in the two-state controller. And I will not talk more in detail about this, but in general, the main idea is that we be able to ensure that the state will have a globally ultimately bound result. And after the final condition has satisfied, we also ensure that estimation error will also remain the globally automated bound result. So the next part, I would like to talk about simulation. So for the simulation, we will use a dynamic of a spacecraft in low orbit using two-body gravity plus some drag or modeling. And the simulation will run for 350 orbit, a little bit long. And for the drag model, we only use the simple Harris-Presler density model. And the rest of these are initial condition and the gain that we use for the simulation. And for this example scenario, I want to emphasize that we're not planning to make this simulation high fidelity. We just want to make sure that it have enough fidelity that we can test our proposed algorithm and make sure that we can demonstrate that our algorithm is actually working properly. So now let's look at the result. So the first result is related to the relative state and control input. So this plot shows relative position and relative velocity and control input and trajectory. I just want to say that for this plot, we be able to show that all the state and control input are converging and they stay bound throughout the simulation. So let's move on to the more important result, which is the behavior of the sparsity and when this concurrent learning activate that make the estimation error go to zero. So these two plots here show the Brakman gain, the adaptation gain, and then this second plot show the lambda, which is the finite condition that we have for activated the concurrent learning. So I would like to zoom in a little bit for the Brakman gain. So you can see that at the start of simulation, it starts from some initial value and it's start to adapt at the first 10 orbit, first become a large value, but then it's convert to some stable value. And at the end of the warm-up time, you can clearly see that there are actually more active term and some of term are not active. So here we can just select the more active term that we want to include for the next stage of the controller. So in this case, we decide to select 8 of them, 15% of it, and the rest of that we just initialize back to zero. And at the end of that warm-up stage, you can see that now, because we also include the concurrent learning term in to start learning about the system, you can see that lambda now grow until it reaches some threshold value that we set, in this case 600. And at the end of that threshold point, you can see that now the unknown coefficient now exponentially converge as predicted by the stability analysis. So the next result that I would like to show is how the estimation be able to recover the differential drag. So in this plot is a comparison between the true differential drag and the estimate differential drag for each of the LBLA component X, Y, Z. And the red color showing the estimate, and then the blue color showing the real differential drag. So you can see that at the start of the simulation, it starts from big value, but it's actually slowly converge to closely track the real drag value of the drag that we have. As I zoom in for the last 10 of it, so you can see that it closely track, although there's still some large mismatch. However, the most important thing that I want to show here is that you can see that the estimates be able to correctly discover that the X and Z component is actually close. I mean, an average is actually zero, and only the Y component that have some negative value, which is the expected structure for differential drag in the LBLA frame that have the negative value in the Y component. And the bottom here is how we reconstruct the formula for the differential drag. So you can see that now the controller was be able to figure out by its own from 54 coordinate and reduce to 8 active candidate term and discover the function for each of the differential drag. And the key important thing here is that you can see that the dominant term is actually depend on the Y component, and then it correctly discover that it's actually depend on the velocity of the chaser in the Y and velocity of the target in the Y, which is actually expected structure of the drag. So finally, I would like to conclude this talk. So in this study, we be able to propose an online sparse estimation technique that be able to discover differential drag from a large library while still be able to ensure the stability result. So the important thing about the controller is that it be able to select the most relevant function starting from a large set of library by its own with almost too little to no tuning. Um, and we see the potential of this controller is that it be able to apply to other unknown dynamics, not only just differential drag. And we make through because it's a Lyapunov based um, method, be able to ensure that the estimation will have the uniform ultimately bound result, and it's rigorously guaranteed through the stability analysis. So for the future work, I would like to improve the library a little bit more to include, for example, the uh, height or the position of the space thrust so that we can improve the model of our differential drag and to be able to extend to other learnable dynamics such as reaction wheels, health estimation, for other things. So that is all for my talk. And thank you very much for your attention. And if you like and have any question, feel free to reach out me to this email. Thank you very much.